When designing a control system, knowing whether it will remain stable is paramount, but finding that out often leads to a mathematical nightmare, trying to extract the exact roots from a massive, high-order polynomial equation. This foundational math is known as the closed-loop characteristic equation, 1 plus the open-loop transfer function, g of s times h of s equals 0. Its roots are the closed-loop poles, and their exact coordinates dictate whether your system survives or destroys itself. Finding those pole locations algebraically becomes extremely difficult when you are dealing with high-order dynamics or systems that have built-in time delays. The algebra quickly becomes intractable. Instead of fighting the algebra, we can use a geometric bypass, the Nyquist diagram. This method allows us to determine the stability of a closed-loop system using exclusively open-loop frequency response data. By plotting that open-loop data, the Nyquist approach saves engineers from impossible factoring. It shifts the entire problem away from complex algebra and solves it purely through visual geometry. This bypass relies on the work of Harry Nyquist and his mid-20th century breakthrough in mapping dynamic stability, created long before engineers had software to brute force the math. The playing field for this method is a two-dimensional complex plane. Here, we map the open-loop frequency response, g of j omega times h of j omega, placing its real part on the horizontal axis and its imaginary part on the vertical axis. As we sweep the input frequency from 0 to infinity, the system's behavior traces a continuous curve across these axes. We can determine the absolute stability of a highly complex closed-loop system simply by observing how this open-loop frequency curve interacts with a single specific coordinate. The ultimate question of system survival reduces to a straightforward geometric test around one vital anchor point, -1 plus j0. Let's map a specific open-loop transfer function. We will use an equation with a variable gain parameter, k, divided by s times s plus 1 times s plus 2. Our mechanical goal is to track the path of this equation as the input frequency, represented by omega, sweeps from 0 all the way up to infinity. This multi-panel guide breaks down the construction procedure. Step 1 is finding our starting point by calculating the equation's limit as frequency approaches 0. If we evaluate the function at 0, the math reduces to a massive negative imaginary value. The curve begins infinitely far down the negative imaginary axis, shooting up from a -90-degree angle. Step 2 is finding the ending point by evaluating the equation's limit as the frequency approaches infinity. Because we have a cubed frequency term in the denominator, it completely dominates the equation at high values. This forces the entire function to 0, so the curve approaches the origin from the positive 90-degree direction. Knowing precisely where the open-loop curve begins and terminates provides the indispensable physical boundaries for mapping the system's overall frequency behavior. Step 3 requires us to determine exactly where this sweeping curve will cross the horizontal real axis. To find this intersection algebraically, we expand the denominator of our transfer function and set its imaginary part strictly to 0. Solving this yields a specific crossover frequency. We then substitute that frequency back into the main equation to find the exact real axis coordinate, completes the geometry. We draw a perfect mirror image of our positive frequency path, reflecting it across the real axis to account for all negative frequencies. Through these 4 boundary tests, an abstract and intimidating algebraic transfer function is successfully trapped as a tangible geometric shape. This plot shows our completed Nyquist contour. Notice the red star resting at the critical point coordinate, -1, 0. Mathematically, closed-loop poles occur precisely when the open-loop transfer function equals -1. Therefore, any encirclements of this exact coordinate dictate system failure. Recall that our curve's real axis crossing point is dictated by the system gain parameter, k, resting exactly at -k/6. Looking at this top chart for a low gain setting of k equals 1, the crossing occurs at -1/6. The curve remains comfortably far from the critical point. If we increase the gain to k equals 3, the crossing slides to -0.5. The system is pushed closer to the boundary of instability. Pushing the gain to k equals 6 changes the chart entirely. The crossing is now precisely at -1. The curve strikes the critical point dead center. This exact state of intersection defines marginal stability. The system is operating on the absolute razor's edge before total failure. Finally, we crank the gain to k equals 9 in this bottom chart. The crossing point pushes to -1.5, fully capturing the critical point inside the curve. This definitive encirclement proves the closed-loop system is now catastrophically unstable. The gain parameter acts as a pure scalar multiplier. It literally inflates the system's geometric profile until it swallows the critical point and breaks the system. This comparison chart breaks down the three main stability tools. When should an engineer deploy the Nyquist diagram instead of root locus or Bode plots? Root locus excels at showing exact closed-loop pole trajectories, making it excellent for time-domain transient response design. The Bode plot evaluates frequency behavior, measuring specific phase and gain margins to test robustness against changing parameters. But the Nyquist diagram provides rigorous, generalized stability determination. It is the only tool robust enough to guarantee absolute stability when the physical plant itself contains open-loop unstable poles or pure time delays. Root locus tracks where poles move. Bode measures how signal strength changes, but only Nyquist provides an absolute mathematical guarantee of survival. We bypassed the mathematical nightmare of solving high-order polynomials, replacing it entirely with intuitive two-dimensional geometry. Closed-loop stability can be perfectly decoded using only open-loop data. The Nyquist criterion transforms a complex algebraic war into a clear geometric question. Does your open-loop curve trap the critical coordinate, or does it let it go?